Cool.
Okay, so I will try to explain the paper how agents should practice. So this is basically kind of reinforcement learning paper. Somehow they kind of have some ideas from how humans learn and everything. So I'll try to see most parts of the paper. And on the future, I think it would be a good insight since I have a plan to explain more into vision language and action kind of papers, like the way how vision is used for, for manipulating things and how vision and language is used for locomotion, action, and manipulation. But this paper might help. So I'll try to go line by line and then be focus on the most important things, but generally, yeah. So let me know if there's any questions. So this would be a paper called How Agents Should Practice. So the main idea of the paper would be, okay, mostly when humans learn something, they are a separate way of like learning. So whenever we have in the match, let's say mostly in the sport kind of scenarios, like in games, in like in match and everything. So we have an actual match, and then we have a separate network called practice. So they play in two separate networks. One is in practice and the other one is in match. So before going to the actual test, we have lots of training and lots of time for practicing the actual match or the actual test. Before going the actual football match, and then we are going to spend a lot of hours practicing with the simulated environment that seems like the actual match, but somehow has some kind of difference. So we'll try to transfer knowledge from the practice to the match in a way that makes the evaluations of the match experience really, that makes the loss of the match really low, or that makes the expected reward of the match time really high. So it's a way of transferring knowledge from the practice to the match. So I'll try to go line by line maybe. So this is intrinsic reward function. So the problem is sometimes extrinsic rewards might not. Okay, what's extrinsic and what's intrinsic? So intrinsic is basically a way of having or learning intrinsically, or it's a way of a self-driven way of learning. So extrinsic is basically a way of learning, but it's mandatory. In the match time or whenever you play football in the match time, it's not intrinsic, it's not self-driven. There are lots of environments, there are lots of people's opponents and stuff. It's a way of learning extrinsically within the outside environment. Whenever it's intrinsic, whenever I just come back at home and then train about the match, train about some basketball shooting and so on, it's intrinsic. It's a self-driven way of learning in a way that maximizes the ability of the actual match time. So we call them intrinsic and extrinsic. So they are basically reward functions. The intrinsic reward function is basically a kind of reward function that really makes good of the practice, and then the extrinsic is basically a kind of reward function that makes the good function for the match time environment. So mostly we cannot find extrinsic. Okay, so during the practice environment, okay, should I use highlighter maybe to, I don't know if it helps, but let me try.
I think it's good.
It's good. Oh, this one is good.
I think you can use a thread. Or do you guys prefer a different one?
Okay. Okay, highlights would be nice. Let's see. Okay. Okay. So during practice, mostly the environments differ from one that's available in training and evaluating extrinsic rewards. That means mostly whenever we are in the practice environment, basically the environment in the practice and then the environment in the match would be different. The environment that we have in the actual test day and then the environment that we have whenever we study at home is really different. That's why, but we can transfer the knowledge in the practice time to the actual match time. So the whole point is basically it's all about setting an alternative periods of practice and objective evaluation. It's called practice and match. So it's a way of alternating the periods from the practice and then to the match, and then it's transferring the knowledge. And mostly we can use in humans playing sports and playing games and so on. So the main point of this paper is basically to effectively use the time in the practice and then evaluate that in a way that improves the actual match. So to effectively use the time that we have whenever we study at home in a way that makes the performance of the actual test really high. So we are going to alternate the policy that we have between the practice and the match. So for this to be possible, there's a way called meta-gradient approach. That's a way of adapting or a way of transferring the practice reward parameters to reduce the extrinsic match reward loss or the computed from the match. So whenever we compute some match, whenever we do some kind of actual match time environment, we have to reduce the loss, or we have to reduce the extrinsic reward loss in the match time by using or by really utilizing the practice time reward, by really adjusting the practice time reward parameters. So mostly on their experiments, they first illustrate on a simple grid world. We are going to see they evaluate this way in a very simple grid world. And also they evaluated on 2 games. So it's in the Pong game and in the Pac-Man game. I don't know if you know the Pac-Man one, but just the Pong game is a normal table tennis, and the Pac-Man one is you have lots of pellets, you have lots of ghosts, and you are going to traverse in a way of like maximizing and eating lots of pellets without being catched by the ghosts. That's Pac-Man. So in the Pong game, whenever we practice the Pong game, the opponent would be a wall. So there will not be another opponent who can actually bounce the ball, who can actually hit in a different direction of the ball, and so on. So it would be just a wall. So there is no, so the velocity will be constant. You know, like I hit the ball and it's zero. So whenever there's an opponent, you can hit it in a very speedy way. You can hit it in a very like not speedy way, or you can hit it in a different direction or something. But in a practice environment, it's just a wall. In the Pac-Man, the practice is basically a maze, but without any ghosts. The actual Pac-Man is basically a kind of environment that has lots of maze, that has lots of ghosts and pellets. But the practice one is basically that with no ghost, but somehow has a pellet. So as you see, the environment, the kind of observation that the practice policies see and the kind of environment that the match policies is really different. The practice observation and the match observation is really different. So why are we doing this? Because like mostly it's difficult to for some kind of extended period, it's hard to get some kind of rewards. I don't know if you remember this, but mostly whenever we have some kind of action, or whenever we have some kind of games, the kind of reward that we are going to get is extended for a long period of time. Or like after we get some kind of rewards, it takes a lot of time to get the second reward. So mostly people do, okay, well, why not? We can have some kind of like learning from the practice and then transfer to the match instead of just waiting for extended periods of time to get one reward after the other. Sometimes it's so hard to specify the kind of reward that we have. Sometimes rewards might not be unavailable in the match time. Sometimes in the match time, the rewards might take an extended period of time. So, and sometimes it's very scarce, or the reward might be delayed or something else. So a range of approaches are possible to have some kind of reward design in a way that can potentially reduce the challenge that we explained above. So one of the way is basically intrinsic rewards. So the agent basically tries to augment or replace the objective of the extrinsic reward. So the extrinsic reward, the objective of the extrinsic reward is basically to give rewards for every possible action during the match time. But the problem is in the match time, we have these problems. We have these sparse rewards. Some of the rewards are delayed, and then we have to wait for extended period of time. And sometimes it's difficult to specify the kind of reward that we have. So among all of the solutions, one of the solutions is to develop a reward design that can actually have some kind of similarity with the kind of objective that we want to fulfill whenever we do extrinsic reward, whenever we try to design match policy. Yep. So basically the aim is to provide useful and good learning signals that drive behavior and learning that improves the performance of the main objective. So it's a way of intrinsic way of learning. So it's basically, we are trying to drive signals in a very intrinsic way. So that can actually make improve the performance of our main objective. Yeah, so the problem is previously intrinsic rewards are mostly hand engineered and task specific, blah, blah, blah. So we have to generate some kind of reward features in a very handy way, but this is the current approach called meta-gradient approach. It's an automatic way of flowing the information from the practice to the match. So in this work, we are going to address the challenge imposed by settings where the learning agent stays for extended period of, we already talked about this. So the whole point is basically in a practice match environment. So we are going to refer a practice match environment. So we have a lots of analogy for practice match as you know it. So like for humans in sports and games, for example, in a team of sports, let's say in basketball, it's common really to practice skills such as dribbling, shooting. So basically, whenever you do basketball match, before going to the match, we are going to learn a lot of separate skills or discrete skills like dribbling and shooting and so on. So, but we have to transfer this discrete knowledge in the match time. But the match time has different kind of environment, right? So the kind of environment that we use whenever we dribble or try to learn shooting is kind of different in the actual match. In the actual match, we have opponents, we have time frames, and we have lots of constraints. So in the absence of the other players, so whenever we dribble, whenever we shoot, there's no other players and stuff. Yeah. So it's common to practice skills in environments other than the football, other than the match court, other than the match time. It's common to learn practice. So it's okay. So yeah. So yeah. So mostly it's common to have some kind of long extended hours of practice. So mostly, okay, I don't know if you can relate about this, but mostly people do in the practice match rewards, mostly people do try to switch off in the evening in the office hours, they make them, learn about practice, and then whenever they are on, they try to act in the actual environments. So yeah. So they for a daytime and anything with this one. So yeah, so we are going to alternate between practice and match, and then we are going to discover good practice rewards. So the primary contribution of this paper is basically generating the reward function. So we have to generate the reward function. It's called intrinsic reward function that can actually transfer a knowledge, or that can actually reduce the loss that we are going to have in the match time. So in the match time, we are going to have some kind of loss, and we are going to minimize those loss by using the reward function from the practice. I think I've read this related work. I am not sure it's important, to be honest. So I will focus on the different algorithms that we have in the intrinsic in the practice rewards. Okay, I don't know if you remember about policy gradient-based reinforcement learning, but I think there are like lots of algorithms for whenever we do the reinforcement learning class. One is value-based methods, the other is policy gradient methods, and the other is another gradients, right? So in the policy gradient-based methods, basically we optimize in a direction that really minimize the our objective function, which is the cumulative sum of rewards. So we want to have a cumulative sum of rewards, and then that cumulative sum of rewards should be high, and then we are going to optimize to the direction that makes the cumulative sum of rewards really high. That's why it's called, it's a gradient-based reinforcement learning or RL algorithm. That's why it's called a policy gradient-based RL. So I don't know if you remember this formula from the lecture. So it's basically computing the gradients for the policy gradient methods. So yeah, this is something that we know from the RL class. So we have different time state T, and then we are going to have state S. We are going to take an action A, and then we have a possible action. So then we are going to use a policy pi that has a parameterized theta, and then we are going to map from state S to an action A. And somehow we are going to end up with some quality distribution of actions, and then we are going to parameterize theta in the direction that makes the expected the cumulative sum of rewards really high. So our objective function is basically making the cumulative sum of rewards really high. And then we have pi, which is the policy, and then we are going to parameterize theta, and then we are going to parameterize theta in the direction of making the cumulative sum of rewards really high. So yeah, so we have a discounted sum of rewards, a discounted sum of, we have gamma, and then we have yeah, so it's a discounted sum of rewards. I think you remember this formula. So from we have a discounted factor, and then we have rewards, and then we are going to multiply the discount factor by the rewards. So yeah, so our objective function is basically having the expected sum of rewards really low. That's our objective function. So let's talk about the notations. So theta is our policy parameters, and then we have two kinds of rewards in this case. We have rewards in the extrinsic, and then rewards on the intrinsic. So rewards on the extrinsic are basically the kind of rewards that we should give for the agent whenever achieves good during the match time. And then intrinsic rewards are basically kind of rewards that we are going to set whenever we do the practice time in the practice time. So it's a way of like being rewards next in the practice and the rewards in the match. So the REX is basically extrinsic reward, and the REN is basically intrinsic reward. But in the intrinsic reward, we are going to parameterize it by what's this tau, right? No. So we are going to parameterize it by tau. So it's basically a kind of parameter that helps us to do
It's called eta.
Eta, okay. So it's called eta. So it's basically, we have two reward parameters, the extrinsic and the intrinsic reward parameters. We are going to see them each and every one is independent. So basically we have two objective functions, JEX and JEN. So JEX is basically the kind of objective function that we have, that's the cumulative sum of rewards in order to that we have in the extrinsic time. And then JEN is basically the intrinsic value policy or the intrinsic expected sum of rewards that we have in the intrinsic time or in the practice time. So our objective is to separately have these two objective functions and then be good in the extrinsic time, be good in the intrinsic time. So how are we going to be good in the extrinsic time? We are going to parameterize the time in the direction that makes the extrinsic matchness really low. And then during the practice time, we are going to parameterize our parameters that makes the practice the expected reward for the practice time really high or makes the loss really low. So our objective function in both extrinsic reward and the intrinsic reward is to make the both practicing match time really have a good expected sum of rewards. That's our objective. But the point is, okay, how are we going to transfer the knowledge from the practice to the actual match? So there's a way of evaluating the parameters that we get from the practice in the match time. And then we are going to feedback those feedbacks of the knowledge from the match to the practice. We are going to tune the parameters in the practice time, and then end up with a good parameters in the practice, and then use those parameters to evaluate in the match, and then have some evaluation in the match time by the parameters that we have from the intrinsic parameters from the practice time, and then we are going to evaluate the feedback range for this process. So let me explain about this paper. So we have two modules basically. So one of the modules is basically something that we are going to parameterize by data. And one is basically practice reward that we are going to, okay, tau, no, okay, it's tau. But we have two parameters here. One of the parameters is theta, that's basically going to parameterize in the match time. And then the other parameter that we have is basically tau, that's going to be optimized in the practice time. So the point is basically the way of optimizing tau in the direction that makes the objective function. Eta, okay. So
it's eta and theta.
Eta and theta, okay.
Yeah.
So we have two parameters here. One of the parameters is theta, which is basically a parameter that we are going to use in the practice time, in the match time. And then eta is basically the kind of parameter that we are going to use in the practice time. So the point is we are going to adjust the eta in a direction that makes a cumulative sum of rewards of the extrinsic objective function we have. So we have JEX. JEX is basically the extrinsic objective or the match time objective. So we are going to update this one, the practice reward eta, in the direction that makes the JEX high, because we want the eta parameters to be adjusted and then end up with a good skills that kind of like flow back to the match time and then have a good match time policy. So yeah, so during the match time, we have REX, basically it's a reward in the extrinsic time. And then we have REN, which is basically an intrinsic in the a practice reward in the intrinsic time or in the practice time. And these are basically rewards. Let's say if I do shooting, I will give I will give it 5 points. If I do dribbling, I will give it 6 points or something. But the point is, okay, I will do dribbling, I will give it 5 points. I will do shooting, I will give it 6 points. The way of giving the rewards basically called REN, which is basically the rewards in the practice time. Now I'm going to optimize the eta, which is basically the kind of way of giving the points or the rewards for the intrinsic time. And then, okay, after using these theta parameters in the match time, okay, it says, this guy is really good in dribbling, but not in shooting. So this is basically the evaluation that I get in the match time. using this feedback, I'll go back in the practice time and then say, the parameters eta was 5 points for dribbling and 4 points for shooting. But now you are good in dribbling, but not in shooting. So they try to manage the eta value or the practice reward values in a way that makes the match rewards really low, or the cumulative sum of rewards for the match time really high. That's the whole point of this paper. So the more interesting part is the kind of experiment that they do. The whole idea is this basically. So the algorithm overview. Okay, so let me look at it in a very close way. Okay, so we have an observation as you know it. The observation would be, they use convolutional neural network to basically, have interpret good embedding from the observations. And then we have an observation, but the problem is the observation and the environment that we have in both of the environments are really different. They're not really the same. In the Pac-Man, we have ghosters. In the match time, we have ghosters, but in pellets. In the practice time, we have pellets, but we don't have ghosts and so. And then in the pong, we don't have we have table tennis, we have opponent in the match time, but in the practice time, we don't have any opponents, just basically a one. So somehow in the practice time, we don't build function at the match time, but somehow we kind of learn generic way of like the generic way of the task. You can actually hit the ball, you're actually seeing the ball, giving the ball back, some kind of generic task, but not that might be helpful for so it might not be helpful for complex scenarios, but it will be helpful for such issues. Yeah. So somehow there will be an observation in the environment, and then we are going to concatenate the observations with practice match flag. Practice match flag is basically, okay, is this observation is in the practice time or this observation in the match time? So this practice match flag basically helps me to know the different policies that I have to use. Because like if I'm in the practice, it's basically different policy. If I'm in the and then the kind of parameters that we have to optimize in different scenarios really different, right? The pi, theta, and the theta, we are using policy gradient, so the parameters that we are going to optimize in the practice, and the reward is basically completely different. So we know, or we somehow need a flag, a practice match flag to know whether we are in the practice match or in the match time. So when we concatenate the input, STP for the practice environment and STM for the match environment. Yeah. So during match, the policy parameters are going to be updated in the match task. It's obvious. And yeah, so during match time is during the actual match time. So it's kind of a match task. So the kind of reward parameter that we have in the match task is called extrinsic reward. And then this extrinsic reward is basically happening whenever we adjust the policy parameters of theta. So the policy gradient method, we are going to adjust the parameters theta in the direction that makes J, so the objective function that we have, or having the gradients of the extrinsic objective function really low. So we have to flow the gradient in the direction that makes, or that follow the gradients of the extrinsic objective or the match time objective. So which is what's the objective of the gradient J is basically it's a discounted sum of match time extrinsic rewards. So again, what's the objective function? It's basically the discounted sum of rewards. So we are going to have a gamma, and then we are going to multiply with rewards, and we are going to add SN. So it's basically the sum of discounted sum of rewards. So for all of the episode, right? So that's basically our objective function. But the problem is, is it in the match time or it's in the practice time? So this is basically a match time process. What about it whenever we're in a practice? Whenever we're in a practice, we have a policy parameters. So we're in the policy gradient method, we have a policy parameters, and we're going to update the parameters, right? So it's a gradient way of updating the parameters. It's not a value-based function right now. So yeah, so this happens by adjusting the theta parameters in the direction of the gradient of JE. So the difference is basically in the match time, we are going to update the policy parameter in the direction of the JEX gradient, right? So JEX is basically the extrinsic time objective function. But in the practice time, we are not in the match time. So we are going to adjust the parameters in the direction of JE, or the objective function of the intrinsic time of the practice time. What is that? Is basically the sum of expected rewards for all of the intrinsic rewards, or for all of the intrinsic time rewards, or the practice time rewards. So this is during practice. Now the actual point of this paper is this one. Okay, after each practice update, Now, okay, I'm in the match time and then I'm in the practice time. Now I have two separate methods for the practice and the match. Now I have to flow the information from the practice to the reward. That's the point. So after each of the practice, before going to the test, after each of the practice or after studying at my home really well, I have to transfer the knowledge. So after each of the practice updates, right? So the intrinsic practice reward parameters are going to be updated in the key meta balance. So I already explained this before. So it's basically a way of updating the reward parameters eta. So the reward parameters eta is basically a way of giving rewards for different parts or for different skills. But it's considered like there are lots of dimensions for different skills, like dribbling, for shooting, and for everything. So I have a value, or I have a score values for different skills that I have. So let's consider we have X, Y, and X for lots of dimensions. And for each of the dimensions are associated to scores. So the thing is, I'm going to adjust not the skills, but the score values, the different intrinsic practice reward values. Okay, how much amount of reward should I give for this specific skill? How much amount of reward should I give for this specific skill? So adjusting this will make the agent to be stronger in one skill and be weaker in the other skill, strong in the other skill, be weaker in this kind of skill. So how can I get this kind of information in the match time? In the match time, we have thetas. Theta is basically the kind of parameter that we have in the practice time. Well, we have two thetas we are going to see, but in the practice time, we have a parameter of lots of dimensions. That's basically lots of parameters, multi-dimensional parameters that are different skills that we want to transfer in the match time. So I'm going to have those skills and then evaluate it in the match time and then see the feedback. And then using that feedback, I'm going to update the eta, not the skills. The eta is basically a practice time intrinsic reward. That's basically a different way of adjusting the scores for different skills that I have. So if I'm really bad at dribbling, I would adjust the score, the intrinsic reward for the dribbling, and then I'll be good on that. So once I have a good skill after the first practice time, I'm going to use those different skill sets and then use on the match time. So we are going to adjust the intrinsic practice reward eta. So the point is the meta gradient objective comes at this point. So we are going to adjust the intrinsic practice reward. And yeah, so in a way that improves the extrinsic reward performance on the match. We are going to adjust the intrinsic reward parameter in a way that makes the JEX, or that makes the loss of our extrinsic objective function, which is JEX, really low. Or we are going to evaluate the skills that we learn, or the kind of parameters that we get in the practice time, and then we are going to evaluate in the match time, and then we are going to compute, or we are going to evaluate in the JEX, or in the extrinsic objective function JEX. Yeah. So this is done by match experience to evaluate the policy parameters that result from the practice update. We have different policy parameters that we get from the practice time. Those are the different skills that we have, right? And then we are going to evaluate those different skills or the different parameters that we get from the intrinsic or from the practice time within the policy time in the match experience. So after that, once we get the feedback, the thing that we are going to update is the intrinsic reward parameter eta in the direction of the JEX, not in the JE. So if you see from the previous one, during the practice time, we are going to adjust the parameter in the direction of the JE, because the objective function is basically the discounted sum of reward in the practice time. And then during the match, it's going to be, we are going to parameterize our parameters in the direction of JEX because we are in the match time. But now we are going to flow the information from the intrinsic to the extrinsic. So we are going to adjust the eta in the direction of the gradient of the JEX, which is the objective function of the extrinsic time, or the match time, or we are going to minimize the loss of the objective function of the extrinsic, which is basically the expected sum of rewards in the practice time is to be had. That's all. We have two variants of this. One is using like offline policy, and then the other one is using online policy. So in the offline policy, after each of the practice, we are going to evaluate the practice reward parameters in the next match. So let's say I have a test tomorrow, And then I'm now preparing, I'm in the practice time, and then I'm going to pass the kind of knowledge parameters that I have to tomorrow, to tomorrow's test. So it's an online learning. So there's an upcoming test tomorrow. The offline learning is basically there's no need to have a match evaluation for the coming future, but what we are going to do is basically we have a policy parameters, we have different knowledge parameters of the skills. I'm going to evaluate these parameter skills on the previous match on the previous match. So this is basically an offline array. So there are two variants of this. The first one is updating based on the previous match experience, which is basically, okay, let's say, I don't know, let's say I have a match, and then let's say I have a practice parameters, and then I'm going to evaluate in the previous match, or I'm going to update it by the next match. That's basically it. So it's basically an online and offline learning.
Wait, what do they mean by next match exactly?
Next match is basically the coming match, or like, okay, let's say you have reply buffer, right? So reply buffer is basically already stored list of match that you already did. So whenever you do the practice reward updates, you are not going to do a new upcoming match, but you are going to use the stored reply buffer in order to evaluate the practice parameters that you had based on the reply. But when it's in the upcoming match, so it's going to be, you have a next match. Okay, let's say the robot is off in the evening, right? But it's going to be turned off in the morning, right? So we are going to test the practice reward by the morning match that we have, by the morning reloaded environment. Does that make sense?
Yeah, okay, so in one case, you consider how your practice would have affected your past performance. And in the next case, you try to estimate how much your practice will impact your future performance.
Exactly. So basically, it's offline learning and online learning. So you try to see about it on the reply.
Yeah, it makes sense that way.
Yeah. So we're going to see, this is basically gradient descent. I really don't know about this formula because like this one is the basic formula that we have in the policy gradient method. So there's one course, I don't know if you know it from the DeepMind, there's actually some technique to convert from this one to the log of the policy parameters. But the whole point is basically the general idea of policy gradients or a policy gradient array. So we are going to have a trajectory DM that's basically the whole episode, the whole starting from S, we are going to do an action A, and then at the same time, we are going to end up with a state S t+1, and then we'll do an action and so on and so on. So you will have lots of trajectories. And then we are going to have a policy parameter pi theta. Those policy parameter pi theta are a way of going from one state to the other and then choose or pick one probability out of our distributions. So the policy parameters or the policy gradient comes by updating the parameters theta, and that parameter theta would not be a value-based function. It would be a gradient-based function that follows the gradient of the thing that we wanted to do. So that depends on the different kind of thing that we wanted to do. In this case, the gradient that we wanted to follow or the kind of parameter that we want to adjust would be in the direction of our objective function, which is if we're in the match time, it would be the extrinsic or the cumulative sum of one in the extrinsic time in the match time, or if we're in the practice, it would be the cumulative sum of involved in the practice time. So the way we are going to update the parameters is basically all the times the alpha times the gradient that we have. So we know this formula, that's basically a basic gradient. So there's actually one technique to change from this formula to this one. So maybe I have to check this one, but generally this is a basic gradient. So the way we are going to update the parameters is basically follow the gradients towards the direction of our basic function, which is the parameter, theta plus alpha times the gradient of our objective function. So this is basically in the match. So during the match, it's basically easy. We're going to update the parameters, and then we have an objective function of extrinsic reward. So in the policy parameters of the practice, we are going to have a trajectory from some step. We are going to pick one action, then another step, we are going to pick an action, and so on and so on. But the problem here, okay, the thing is here we're in the practice environment. So we have, along with each of the environment, we have a flag, whether we determine the match, whether we're in the match or the practice. That way we know we have two different policies, right? So we are going to update two different parameters. Here, it's considered theta double parameter. It's going to update theta prime. and then it's going to update in the direction of our intrinsic objective function or our practice time objective function. So this is basically updating the policy parameters during practice and updating policy parameters in the match. Now the point is, okay, we are going to update the intrinsic practice reward parameters. So bear in mind that we are updating not the parameters of the practice time, but we are updating the intrinsic reward parameters, the way that we reward the different skills that we have in the practice time. So it's eta, not the theta double complement. This theta double complement is the practice parameter that we have in the practice time. We are not going to update that. The point that we are going to update is the kind of way that we are going to get the scores of theta double complement, right? So the whole point is we are going to update the intrinsic practice reward parameter theta, but where do we get that information? From the match time evaluation. Okay, this guy is really good in dribbling, this guy is really good in math, this guy is really good in biology, but he's not that much in chemistry. So adjust the score parameters that in the chemistry skills. So theta parameters, the double complement of the different skills, the multi-dimensional different skills that we have. We are going to adjust those different skills in the direction of the intrinsic, in the intrinsic J-in or objective function. But the way we adjust the score, so the intrinsic parameter was basically given from the information from match. So the intrinsic practice rewards tau, eta, are going to be updated in the direction of JAX for the match. So yeah, the gradient of JAX of the match is going to be with eta. It's computed by channel as follows. So eta is basically we have the previous eta times b parameter, and then this one. So this would be okay. Whenever we parameterize eta in the direction that in the gradient direction of the JEX, but JEX double complement means, okay, here's how it works. So JEX is basically the objective function of the extrinsic time reward or the match time reward, right? So JEX is our objective function for the match time. But if you see the parameter is theta double complement, that means JEX theta double complement means we are going to evaluate the performance, the match time performance of theta double complement. The theta double complement is a parameter that we get from the practice time. That means we have a lot of skills. We are going to bring that lots of skills, and then we are going to fit in our objective function JEX and what with the parameters of the practice time. That means we are evaluating the match time performance of our different sets of skills that we get from the practice time. So the theta double complement are the different parameters, and we are going to add into the JX. But after the JEX, we are going to update the eta. So that means the eta is going to be updated in the direction of tuning the etas in a way of, like the JEX theta double complement is really high, or the expected sum of rewards in the match time is really high. But how are we going to evaluate it? Using the practice time parameters. So using the channel, we can actually divide it into two ways. So this means, okay, the eta plus, bear in mind, so we're going to follow the gradients of the eta of double complement. That means we are going to adjust the eta or the way of giving the score. So theta double complement of the different skills, the dribbling, shooting, and everything. So we are going to optimize the eta or the different way of giving the scores for each of the skills in a way that makes the skills really good. But that we are going to optimize the eta in a direction that makes the extrinsic or in a direction that makes the match policy really high. So two things. The channel of two things. We are going to optimize eta in a way that makes skills or the different skill that's really high. And once we get those skills really high, we are going to use those skills and optimize those skills to a direction that makes the JEX or the commit server reward in the match time really high. This is basically something that we already talked about. So we are going to evaluate theta double complement the different skills in the match time, and we are going to see those feedbacks, and we are going to update the eta in the practice time, update the eta in a way that makes the different skills really high, and then use those skills, and then again evaluate it in the match time, in the match time. Yeah, I think this is basically it. This one is okay. So the second term, this one evaluates. Okay, sorry. Okay, the second term, this one, which is basically this one, is going to be evaluate. It's going to evaluate the policy parameter theta double complement. That means it's going to be from the practice update. So the theta double complement, we get the theta double complement from the practice update using the intrinsic keywords. By using the eta, we get the theta double complement. And then we are going to evaluate in the match samples. So this means basically it's going to be evaluate the policy parameters of the practice time policy parameters using the match time samples. So we're going to use this in the next match or in the previous match. So it will be in the offline learning or in the online learning. We can use the previous matches to evaluate the practice reward parameters, or we can use the next match to evaluate the match time performance. Okay, I don't remember this one to be honest, but let me clearly explain about the algorithm, and then we'll go to the experiments. So yeah, we will have different experiments, different parameters, alpha for the match, alpha for the P, and then beta. I don't remember what beta is, but these are the different parameters that we have. And then we are going to initialize theta and pi for different random values. And then here it goes. Okay, first we are going to update the policy parameters during match. That means we are going to have a trajectory for a certain episode, and then we are going to approximate the policy in the direction that makes the gradient, or in the direction that follows the JX, right? So after that, we are going to update the theta parameter, which is theta plus this, like this. It's basically easy, right? So the next step would be updating the policy parameter during practice. We're going to have some trajectory, and then we're going to approximate our gradient for the intrinsic objective loss. And then we're going to update the parameters of the practice time parameters in the direction that follows the JEM. So the next would be this one. So we have two separate network, one for practice, one for match, and then we are going to flow the gradients, meta gradient approach. We're going to flow the gradients of the practice and match. So we're going to approximate this one. This one would be adjusting the actual practice time parameters for the JEX. This is basically the evaluation part. And then we are going to approximate this one. This means we are going to approximate beta to make the practice, or to make the skills really good, the n-dimensional skills that we have in the practice time. And then afterwards, we are going to channel them. We are going to multiply the eta and then the theta parameter in the evaluation step. And then we can actually update the eta by using this. This means, okay, it's eta and that's JX. So the eta is basically, we are going to optimize the eta in the direction that makes the extrinsic match loss really good, or the expected sum of rewards for the match time really good. But that's going to be evaluated by the practice parameter. So this is the whole idea of the paper. Now we can go to the experiments. Do you have any questions so far about the algorithms and so on?
I don't.
Okay.
I think
Yeah,
it's
me
pretty
either.
clear.
Sorry?
There's a lot of notation and stuff to follow, but the concept not good.
Yeah, okay. Yeah, it's basically the whole idea is basically, yeah, we have lots of parameters. We have two different objective functions, extrinsic and intrinsic. And then the thing that we are going to optimize somehow differs, because like in the intrinsic time, it's intrinsic time reward, which is REN, that's for the practice. And then we have REX for the extrinsic time. The point comes whenever we want to transfer the knowledge from the practice time to the match time. So we are going to parameterize beta in the direction that makes the match policy of this really high. So it's basically a policy parameter, and then and then a meta gradient approach to flow the information from the one to the another. So there are some important points from here. I would try to be fast and at the same time try to cover most of the aspects. So they try to do the experiments of this approach into two main things. One of these is one simple grid environment, and the other two is basically two Atari games. One is Pac-Man, one is Pong. So let's start with the grid world, and then we'll do the experiments afterwards. Mostly the evaluation starts from here, so we start from this point. But the grid wallet is basically a simple grid wallet. So it's basically a 1D grid wallet. So the 1D grid wallet looks like this. It's a corridor wallet. So the agent starts from T and then goes to B. The T is a trash and the B is a bin. So at X0, it starts to pick the trash, and then at B or at X7, it starts to sort the the trash. So it's a simple corridor wallet. So the whole point is start from here, go to from T to B. So we're not going to illustrate the algorithm in a simple wallet, in a simple grid wallet. So it's going to start from X0 and then goes to X7, and then it starts the corridor environment, has a bin, has a trash, and the whole point is basically to go from X0 to X7. So now the inputting observation is somehow different from the Pokemon in the Pong and the Pac-Man. So here we have a corridor environment, a corridor block, a 1D corridor block, and then another flag that tells us whether we are in the practice or in the match, and then another flag that tells us whether in the trash or whether we are in the whether the agent has a trash or not. So okay, we have a state input, which is basically corridor environment, and then we are going to have a trash or not, and then we are going to flag the practice in the match. This is one of the environments. And then as you know it, whenever it starts from the trash to the bin, it's very easy. So if the agent starts from the trash and goes to the bin, it gets +1 reward for delivering the trash from the can from the trash. But the problem is it doesn't know to go back from the bin to the trash and pick another trash and go again to the bin. So they explicitly mentioned that for the first reward, it was really easy because like we observe that the agents can quickly learn to get the episode +1 by starting from the trash and goes to the bin, but it gets 100 match to go to the episode 2. So if you see it from this point, so this is the number of match, this is a kind of reward per episode. And after a few match, they can get the first reward. That means they can go from the trash, the B, the corridor. But they wind up lots of match to know for the agent to go from the bin to the trash and pick up and then go to the bin again. So it kind of was hard to figure out for the agent that going back to the trash and then pick it up and then going to the bin really gets a reward. That's why there's lots of match difference between the first one and so it takes 100 match. But after the 100 match, as you see it was really frequent, right? Yeah, so this is the idea. I think most part of this, I don't think it's important, but they are ranking and stuff. So yeah, the visualization is basically intuitive and stuff highlights intrinsic dependent. Yeah. So now let's go to the evaluation because the evaluation is the most important part here. So we have 2 Atari games, the Pokemon and the Pac-Man, and then okay, we are going to test 4 things, right? We are going to test 4 things. So one of the thing is basically okay. Does a learning practice environment okay? So we are going to go to the test tomorrow, and then I'm going to prepare today, right? So, and I want to flow the information from the today's test to the tomorrow's test. So they say what they are trying to say. Okay, what if we literally ignore the practice environment and only focus on the match, only focus on the test? That's really helpful. So what they're trying to say is, okay, what is the output or the importance of adding the practice time environment and then transferring knowledge to the match? So does learning the practice environment in addition to the match improve the performance comparing to the match only? So they have one baseline, which was match only. So they try to calculate the objective function by match only. So they will not transfer knowledge from the intrinsic time. So they will not transfer the knowledge from the eta to the JEX or the objective function. They just use the objective function and they just tune the parameters of the extrinsic reward parameters or the policy parameters that we have in the match time, and nothing. They don't do practice. And they compare with the practice time reward that transfer with the match only. So their baseline was the match only performance. So one is this comparison. The second one is basically, okay, is a meta gradient habit for improving the practice was really helpful. So if you remember, one thing that we do is basically we're going to optimize eta in the direction that makes the extrinsic reward loss really high. But what if we don't update it? What if we just set fixed random practice reward? What if we just set fixed eta? So that fixed eta is basically we're not going to update it. It's completely random. And then, but we have a practice and a match, but there won't be any update. And then at the first, the practice eta, the practice intrinsic reward parameter eta would be random. So this would be a way of proving that the policy gradient update from the practice to the match was really helpful. Because like in the practice, we're going to optimize it, and then we're going to evaluate it in the match, and then we have a feedback, goes back to the intrinsic, and then evaluate it, goes back, and then goes back and so on. But what if there is no any, tuning or any updating in the eta, in the intrinsic reward parameter? That means we are not going to adjust the kind of skills that we have. The match says this guy is really good in dribbling, this guy is really not good in shooting. And then we came back to the practice and then update the intrinsic reward parameters or the the scores that we have for different parameters that we have or for the different skills. Here, we are not going to update that. So that means that there won't be any change. So they try to see the difference between the meta gradient update and the fixed random practice reward. So we are going to have a fixed eta value. So this is the second one. The third one is basically, okay, what if we are going to propose a meta gradient eta, but instead of having a practice reward, what if we, let's see what's the match time extrinsic rewards. Yeah, okay, this is really, really awesome. So what they are trying to say, okay, instead of having a practice time reward, what if we create a separate practice time reward, but somehow it's similar to the match time extrinsic reward? So in the match time, we have extrinsic rewards, right? We have a way of like adjusting the different rewards that we have in a way that makes the objective function of the match time scores or skills really good. But we are going to create a kind of network or a kind of intrinsic reward parameters that are not look like the practice, but that exactly looks like the extrinsic reward parameter that we found in the match. So this is a side way of testing. So the first one is basically
wait. So just a question.
Okay.
So this 1.3 basically imagining imaginary ghost while running through the maze.
Sorry.
The point difference, and you said you want your intrinsic reward to resemble the extrinsic one, so you can practice as if you were having a match.
Exactly.
But the thing is, you define practice as not having access to the reward of the match. So I'm wondering, how does this look like for the Pac-Man example? Do you imagine some like imaginary ghost, or you just try to not walk back your steps because you assume that someone is following you or something like this?
Yeah, to be honest, this one is really, really something that I completely didn't understand, to be honest. So maybe I'll try to in the experiment, and then if we solve it, it's okay. But otherwise, I think this one is really something that I completely didn't understand.
So they don't extend this one in the paper. It's just something they throw here.
No, I think they explain it really well. So they explain it in some parts, probably here. So we'll try to see it around here. But whenever I read it, I also had the same kind of question. So it was something that I didn't understand, but we'll see and we'll try to see that around here. They explain it around here. But yeah, they generally had the same question for this one. So somehow it really doesn't make sense. Yeah. But yeah, that's really somehow really straightforward, but this kind of makes no sense. And the fourth one is basically okay, so how does the performance obtained from the practice match compare to the performance obtained? Okay, so this is basically this one is the most interesting one, I would say, from the four. So it says, okay, what if we don't need any practice any practice match kind of compare. What if we give additional time for the match? Instead of having a practice time of like 2 way of like creating and going back and forth, what if we just extend the amount of time that we have in the match? This really makes sense because like, okay, in the Pong kind of environment, it makes sense. Because in the Pong, because remember that the practice environment and the match environment is really different. In the match, for the Pong, we have a tennis, but we have an opponent. So lots of things are really different. In the match, in the practice, we have no any opponent. It's simply a wall. So that means we can actually know how to hit the ball, how to hit the tennis ball, but somehow there are lots of things that we don't know. And it somehow makes sense because the main parts of the policy is not really dependent on that. But in the Pac-Man, if you don't have any ghosts, it doesn't make sense. So in the Pac-Man, we have 2 environments, like practice and match. In the match, we have pellets. Some of the pellets are basically consider them as a fruit that the agent tries to eat. And then somehow the agent tries to escape the ghosts. In the practice time, we have pellets, but we don't have ghosts. So they say in such kind of complex environments, the actual and main policy is dependent on the ghosts or on some parts, on the core parts of the environment. That means if we don't have ghosts, it doesn't make sense. So having a practice for this case doesn't give us that much skill. That doesn't transfer that much skill from the practice to the actual match. But if you give it a large time for the match, it really makes sense because we need the match environment, a full match environment. We need the ghosts because like the whole idea of the Pac-Man game really, or the policy of the Pac-Man game somehow depends on the ghosts. So the fourth evaluation says, okay, instead of having a practice and then match compare, what if we don't have any comparison? And what if we just give additional time for the match? This really makes sense. So we'll try to see in all of the experiments that they did. To answer the first and the fourth question, to answer, okay, parameterize. Okay, I think it's better to remember this thing. Okay. To answer the third question, I think this was your question. Let me check. So to answer the third question, a design method where the intrinsic rewards using the practice come from the method that's trying the okay, this is essential approach. I don't remember this, to be honest. So somehow they say the intrinsic rewards in the practice come from a network that's trained to predict the extrinsic rewards during match. The extrinsic rewards during practice come from a network that's trained to predict the extrinsic rewards during match. You see, I still don't get it. Yeah. Let me know, Martin, if you get this there for the third one. But they propose this, okay, the way of training the way of getting the practice rewards, way of like predicting the extrinsic rewards during match to get the intrinsic reward parameters. This is the way that they propose that I still didn't get. So 2 domain way for evaluation, the Pong and the Pac-Man. So in the Pac-Man or in the Pong, in the environment like Pong, we have a wall, and then the opposite side of the agent is the opponent, right? We don't have any opponent, we have just simply a wall. But in the Pac-Man, we have a maze, and then without any ghosts, right? So in the practice time, we won't have any ghosts, just basically a maze. We shoot some pellets. So ghosts are going to be avoided in this case. So after every match, the agents are allowed to fix a time for practice in the practice environment. So after every shot in the match, the agents is going to be, sorry, they explicitly give an example that says, whenever we do the evening time or whenever the match time is ended, we are going to do some time of extended time to do the practice or to do some practice training. So in each of the experiment, they do specific time. They explicitly mentioned specific time. Let's say in the Pong, the agent practice in 3,000 time steps after every match. So there's an alternative way of practicing match time of training. So after every match, we are going to give it 3,000 time steps to train for the practice. So some like they do after every episode or after some certain kind of match time episode, we are going to give time for the practice to adjust the skills by using the evaluation that we use on the extensive words. So there are specific times for the practice time and then for the match time learning. So this explains the details in the implementation. So they mostly use open source Actor-Critic agents. I don't know if you remember Actor-Critic agents, but if I remember correctly, there are three methods, right? Value-based methods. And then I want to compute the value function for every action that we choose from being a certain state, right? So what's the possibility or the value of being in a certain state, or what's the value of choosing a certain action? So we're going to compute the value function. And then there are other methods called policy gradients. So it's a way of smoothing the gradients to find the actual or the good policy parameters. So we don't do this every time we do the value functions. We just optimize the parameters to the direction that gives us a good something, a good objective something that we want to. That's policy gradient. And I think there has been some problems regarding the policy gradient methods. If I remember correctly, there has been some problems in the variance of the policy gradient methods. And there are some core reasons that we still want the value-based methods. So they designed an Actor-Critic agent. So an Actor-Critic agent is basically in the middle of the value-based and the practice ones. So we have an actor and then we have a critic. So the actor tries to find a policy based on the policy gradient methods, and then we are going to evaluate those policy parameters using a value-based function. So Actor-Critic is basically the mix of both or the mix of both the policy gradient methods and the value function methods. So mostly for this implementation, because they use Actor-Critic agents, that's from the open source OpenAI implementation, and they use that. And yeah. Okay, so Actor-Critic agents perform and so on and so on. So yeah, instead of waiting for the next match, we already talked about this. So instead of waiting for the next match, we store the previous match, right? So we are going to evaluate the updated parameters from the practice time in the evaluation time that we had from the previous stored match values, right? So we don't need to wait for the next match. We basically store the previous match in the buffer. And then we are going to evaluate the practice time policy parameters by the buffer or by the stored match samples. And then by those, after we evaluate those, we are going to update the policy parameters. No, the intrinsic UI parameter eta by the evaluation that we get from the buffer or from the stored evaluations or from the stored match samples. This is one way. And yeah, we already talked about it, but like we have pixel values and then practice match flag. For all of the observations, we are going to use 2D pixel values. For the corridor, it's a 1D. For the Pac-Man and for the point, it's going to be 2D, right? So it seems it's a 2D game. So we're going to pass those observations to convolutional neural networks to have some flattened out embeddings. And then we are going to pass those flattened out embeddings to Actor-Critic agents and learn actions from there. It's pretty easy. So the input of the observation will be the games. The games would be passed to the convolutional neural networks. And then after that, after some convolution, we're going to flatten out those are embeddings. And then we're going to pass those embeddings to Actor-Critic agents to learn actions. Basically, Actor-Critic agents learn value-based policies. In a way, how can we act for a certain state, how can we do, or how can we pick some kind of action from a certain distribution of actions? And then that should be follow the guidance of the objective function that we wanted to pursue. That we have a flag practice match to learn different kind of policies. Yeah, that's basically it. So there should be a visual mismatch. There should be a visual mismatch between the practice and the reward. That's how we are going to learn two different policies, right? So the kind of visual representation that I have now and the kind of visual representation that I'm going to have tomorrow when I have a test is really different. But the kind of transfer the skill that I'm going to study today for tomorrow's test. So there should be a visual mismatch between the practice and the match. And as we note, whenever some kind of big visual mismatch, it kind of affects the performance for some kind of games or for some kind of agents, because some parts of the visual representations are really helpful for the agent, because the core part of the policy learns from some parts of the visual representations, like the Pacman game. Yep. Okay, so these are basically the learning curves. These learning curves are basically for the Pong. So for the Pong in the match environment, as you see, there are two opponents. This is basically the ball. But in the practice environment, there's basically a wall, and this is one is one of the opponents. So yeah, in the number of matches and the number of time steps. So we have 4 different results: the blue one, the red one, the green one, and the black curve. So they basically perform or track the performance in the after click agents only in match. Okay, so the blue one is basically only in match. So as you see, the blue one is this one, and the meta gradient practice one is the red one, and the random review practice. The random review practice is the one that we are going to randomly set the eta value or the intrinsic reward value. So instead of basically having an updated meta gradient approach, we are going to set some fixed eta value. So as you see, the random review practice one is really low accuracy in relation to the others.
But it's funny that at the beginning it surpasses the only match. It's like random practice at the beginning can be better than like actual gaming.
Yeah. So yeah, that's why we get a good accuracy in the beginning of the random practice, the random intrinsic parameters. So only match shows basically only match time. There won't be any practice, just practice time. No, it's just only match time. There won't be any practice. Somehow it's good, as you said. The blue one is good, but the red one is really, really better because we are going to transfer it from the one to the other. But the thing is, during the Pong, only the match should be better than the meta gradient approach, because only the match means we are going to have extended period of match time learning. So that should be a good performance than the practice time. So in the Pong, you are going to see the accuracy of the only match. Okay, the only match is really bad. The one with the weight is the meta gradient. Which one is really good? Okay, it's in this one. Okay, only match. Okay, the blue one. Only match. I have to read this one, but only match should be high because like we are going to. Okay, this one is the Pacman. Only match should be really good. Because like, only match means we are going to train it in the extended period of time. That means we are going to, like have all the visual representation of the Pacman, even the ghosts and everything. That really makes it really good accuracy. So I'm going to explain this learning curve in these results. Okay.
One point also, their reward prediction method looks kind of shit, honestly.
Which one?
The black one. That's the point 3.
The black one.
Yeah, they say they wanted to estimate the extrinsic loss using a network to have some practice that resemble the match, etc.
Exactly. Yeah, it didn't perform really good.
It kind of looks like a flop.
I don't know. I didn't understand it, to be honest. So we're going to. I don't know if I have to explain the details of this graph, but let me try. So yeah, we are going to run with 2 experiments: the Pong experiment and the Pacman experiments. So these 2 experiments means the setup of the experiments, and this part should explain the kind of results that you get. So we have 4 settings. One of the settings, okay, we are going to have a Pokemon and Pacman game that's basically done onto the active critic agents. And one of the active critic agent was only match time. And the other would be active critic agent that learns from practice in the match, borrows from the practice in the match to be the actual proposed method, the meta gradient approach, passing the knowledge from the one to the another. And it's called a meta gradient practice. And then we're going to have active critic agents that learns the practice in the match, but using a fixed time reward parameters. That means we're going to have a fixed parameter values for the intrinsic reward parameters. And the last one would be the active critic agents. Yeah, this one is the one Martin said. So it should be a practice reward, but how the ETA is learned from the extrinsic from the prediction of the extrinsic reward parameters. So how does the Pong experiment look like? So we're going to explain about the different kind of experiments, and then at the same time we're going to explain about the results. So you know about these experiments. I think we already explained about these results, but it says, okay, it's a table tennis game, and it's the CPU player and the opposite side. So the two-player game, the CPU and the opposite side. And then we're going to reach 20 points. I don't know if you played Pong. I think Imran is very good in the Pong games. There are 20 points. The agent should reach the next.
Really, actually.
So the number of points that we are going to get from the opponent side, for one opponent should get like 20 points to finish the game. So this is basically the cumulative expected sum of rewards. So it's, yeah, the sum of rewards should be, no, I don't know what I'm talking about, but it should be 20 points to finish the game. So the point is, there is dynamics in the match time. In the match time, there's dynamics. There's angle, there's a ball like bend over whenever the opponent hits in a different direction. There's difference in the velocity of the balls and so on. So this won't be happening in the practice time. It's just a fixed ball. There won't be any angles, directions, and so many complicated stuffs. That's simply straightforward ball. And then the whole point here is sometimes there might be some skills that we have to learn. They might not really fit the actual match time, but somehow there are some skills that we learn. So let's say, okay, in the match time, in the match basketball time, there are lots of skills, but dribbling might be one straightforward skill. Yeah. So that's the point that they raise the Pong experiment. So in the practice environment, what should we have? In the practice environment, there's no opponent, just simply a wall. And that means in contrast to the other one, there will not be any, like any accelerations, and it should be constant. There won't be any complex things in the practice time of the Pong experience. To perform well in the Pong, yeah, I think we know about these things already. So that's already, yeah. So the point is, after each time step, after each 3,000 time step, after every match, we are going to give 3,000 time step for the practice. So for the Pangman experiments, they have to give 100 time steps after they're going to give 3 practice episodes after every match. So this is basically a way of like training the both of the networks, and they flow the networks after some time steps or after some episodes. So this is the Pong experiment, the Pong environment, and this one is a Pacman experiment. So the Pacman, as you know it, the Pacman has a lots of pellets. These are the pellets. I don't know, in Google there are Pacman in the game. So yeah, so the pellets are stationary, they don't move much, but the ghosts move, and then they try to eat the agent. So we have to, the point is basically avoiding the ghost. So the practice environment would be just pellets, and then just go and eat the pellets, and that's it. So we are going to learn some skills by going and then eat some pellets, but the whole point of this game is try not to be crushed by the ghosts. So they say, okay, while the practice environment allows the agent to learn navigate. Okay, this is the point, by the way. So in the practice time, the agent will have the opportunity to to navigate about the maze. They don't understand that much about the ghosts in the complex environments, but somehow they understand about the entire framework of the maze and how to eat the pellets and so on. But they say, okay, the ghost's position is the main thing in the pattern, because if the ghost come this way, I have to go that way. So the way of adjusting the policy, the core point of adjusting the policy parameters in the pattern depends on the ghost. So let's talk about the experiments or the results that we get from the Pong and the Pacman. I think we already explained about, but we have a weight curve. So we see the weight curve. The weight curve is basically, we have a blue curve. The blue curve is only match. The red curve is the meta gradient approach. So it says, okay, it performs faster in a match, the blue curve performs faster. So it answers the first question, right? The first question say, okay, the first research question says, okay, does match only is good, or does the practice reward is good? So as you see, the blue curve is really faster than the red one, right? No, the red one is really faster than the blue one. That means having an alternative way of like practicing match really be good than only having the match, only the match. Okay, so yeah, this is in the basketball, tennis, and so on. In addition to the scenarios and the match affecting themselves will be available and so on and so on. Okay, figures 3C and 4C shows clearly about the meta-gradient update. So now we're not talking about the practice in the match, but the update, the way of adjusting the eta in a direction that follows the objective function of the JX, the update. So the update is really important. And the figures 3C and 4C explain 3C this one, and 4C 3C and 4C explains the meta-gradient update. So having a fixed random practice reward, which is a green curve, the green curve, the green curve, the green curve, this one is really bad than the blue curve or the green curve. Okay, yeah. So they perform really poorly, right? So it shows that the red curve, it answers the second question, because like it says the constant non-updated eta values doesn't really have anything. So we are not going to flow information from the match to the to the practice. I don't understand this one. The third one, I believe this one is the third one. And in the Pong, okay, what did I miss? So in the Pong, the baseline performs worse than our proposed method. So the baseline is basically the match only one. So performs worse than the red curve. The red curve performs really good. And yeah, what else? This is interesting. Infinite lifetime policy. I don't know if there's further study counts and the purpose. I don't know if I miss anything about this one. We have seen, but I don't know if I miss anything. So I will we have seen a part types match. We have sales blue curve. What's this? Yep. So yep. So the whole point is basically whenever we have extended match, you can see the blue one here. So the blue one here really goes really good accuracy than the red one, right? The reason for this is because like, okay, having an extended time for the match really is good than, okay, this answers the question 4, by the way. Yeah, it says answers the question 4. The question 4 says, we don't need a practice match kind of way. We just need to give an extended period of time for the match and that's it. But for some environment, the practice can only learn some skills, but the policy dependent on the critical aspect that we found in the match. There is no any point of studying today. Just go there, focus on give the students lots of time to do the exam, and then they will do it. There is no any point of studying today. That's the whole idea. So that means if we would be exposed to lots of hours of exam time, you can make the exam. In some scenarios, it works because like the main or the concrete part of the policy parameters are dependent on the match time settings. That's why here only the match, the blue one, performs really good than the red one. Even though the meta-gradient approach is really good, the main proposed approach is really good, but for some environment, only match or only having an extended period of match really perform really good. Which is the whole paper, but I have to quickly explain about the algorithms and the agent structure, the corridor environment, the training details, and everything. So for both for the grid-oriented and for the Atari games, as you know it, for the algorithm, I think they use reinforce. Reinforce is a variant of policy gradient method, no, arithmetic method. So I think before arithmetic agent, there was an algorithm called reinforce. It's basically a composition of value-based and policy-based gradient method. So the agent structure for this grid-oriented was just to use 3 networks, 2 hidden layers, and 64 units. 64 units means the embedding size or the flattened out embedding size. So they are going, and then we are going to have a tanh activation function at the end and stuff. So they show how do we change the observations, pass through some convolution, pass through some flatten. So in this case, we don't need convolution since it's a 1D corridor. The grid order is basically a 1D corridor, but we need to hit it there and 64 1D flatten out vector, and then we are going to learn the policy and then end up with a tanh activation. We already talked about the corridor environment, external, it gets a UART +1, it has the agent receives the state, which is basically the environment, and then it concatenates the position, whether it's in the trash or in the bin, and then it has a flag whether it's in the practice time or in the match time. So for the training details, they use IDAM optimizer, and then and so on and so on and so on. And then again for the ATRA experiments, they use ActorClick agents, both for the Pongman and for the Pacman agents that was open source from OpenAI ActorClick agents. For the as you know, the ATRA games, both the Pongman and the ATRA, the Pongman and the Pacman is 2D, so really convolutional neural networks. So for the architecture, they used 3 convolutional neural networks, and then end up with a fully connected one. And convolutional layers cost 62, 64 filters respectively. Filter size of 8x8, 4x4. This will be the ordinary convolution, the filters, the feature maps, and the convolution, and so on. And then we're going to add random activation function at the end of the fully connected embedding. And then for the practice and the match, it's going to be a 1 hat vector. So we are going to add a 1 hat vector at the end of this flatten out vector that we get from the convolutional neural network. So we are going to concatenate the vector of the flatten vector of the observation or the state, and then there should be 1 hat vector that explains the flag between the practice and the match. So we are going to pass those to the ActorClick agents in order to learn the policy parameters by that follow the gradients of the objective function that we wanted to do. So this basically shows the training details. The Pong match, the environments came from some of the implementations called Pandan. It's basically an open source implementation of the Pong and the Pacman environments. And they do standard pre-processing, as you know it, and some observations, 4x4 and 3x42. The kind of dimension that we have for both of the environment, where 84x84 for the Pong and 42x75 for the Pacman, and then I'm going to pass for the combination.
I think the rest is details, honestly.
Okay. So yeah.
If we skip to the thing, it's like numbers, training parameters, etc. It's like
translation study.
This is a paper. I didn't remember most part of the paper, but somehow this is it. And I don't know if it helped much, but there has been some people doing on this like intrinsic driven way of learning, and then somehow learning the agents in this way of practice match kind of way, and yeah.
For when is this paper? Like, when was it published?
I think 2019. Check.
2019, okay.
It was a 2019 paper.
Do you know if this approach with the practice match has been applied to other stuff? Because I mean, the examples they used, they have like, I think, a pretty straightforward implementation of this method, but with other things, it might be a little bit more difficult.
You mean for the other environments, for the complicated environments and such? For learning complicated, I mean, for teaching complicated agents for some complicated tasks, yeah, it might not work, but generally, if you see from the way of like humans learn, it kind of makes sense, because like whenever we do some real world events, we have some tremendous amount of hours to practice and learn and cognitively map several things about the actual thing. So from human way of learning, it kind of makes sense, I would say. But as you said, for complex environments, since the environments kind of differ, there would be a huge gap in the the way of learning the policies, and transferring the policies from the practice doesn't make sense because we don't need it at the end of the day, because the policy for that match is really complex, and the kind of skills or efforts that we are going to add by using the practice really will be minimal.
I think
So-
RL is in kind of this weird space where you can have some theoretical work that are very effective, like the one we saw in class, the foundation.
Mhm.
But I feel like they're still limited to very easy models,
Mhm.
which don't go much further than like basic games.
Mhm.
But the general architecture of just the agent interacting with the environment, we can see it can be not improved, but it can be endowed with a lot of different variations like this one. You had practice, intrinsic, extrinsic, etc.
Mhm.
But I feel like it would only make the theoretical study even harder. So you have even less guarantees, and we can see that even the most basic of cases are only used in very basic games.
Yeah. Yeah.
It feels like it has a lot of not potential, but there's possibility to use a lot of human knowledge. I don't know if that makes sense.
Mm.
Like you said,
Yeah.
some way of learning makes sense for human. We'd want to implement that in the method.
Yeah. True.
But the basic method is already so complicated itself that we don't really know where we're going besides examples for Pong and Pac-Man without ghosts or
Exactly.
something like this.
Exactly. Yeah. Yeah, plus as you said, I mean the experiments are really too easy, and I'm not really sure whether they are really scalable or whether they are really important for other complicated stuffs. It seems really hard to just transfer the knowledge from the practice to the actual match policy. But I would say, yeah, as you said, from the human way of learning, generally in terms of idea, it really makes sense. But yeah, that should be something that I have to figure it out.
I don't know if you
Okay.
guys have some
Wait,
other
1 second.
examples for yes.
I think I'm just gonna stop the recording now, or do you guys want to say anything else that should be on the recording?
I think we can
It makes
cut.
sense to end it here.
Yeah, okay.